So here in today's video, we have this integral right here, this really scary and interesting looking integral right here. The integral from 0 to pi over 2 of sine of x times the natural log of sine of x times the natural log of cosine of x divided by cosine of x squared. That's a lot of trig functions, especially now that we're dealing with a trig function inside of a natural log function. So this is going to be interesting. We're going to have a lot of fun with this. Don't be scared of just of this integral. It actually comes down to a finite answer. So that's what we're going to do for today. So let's go. What I'm going to do first is I'm going to define I to equal this same integral. So 0 from pi over 2 of sine of x, natural log of sine of x, natural log of cosine of x. I feel like I'm being repetitive here. All divided by cosine of x squared dx. Oops. What is that I just wrote? Then, what I'm going to do is I'm actually going to do a u substitution. So I'm going to let u equals cosine of x. Then du is equal to negative sine of x dx. Then divide the negative to both sides. So then we get negative du is equal to sine of x squared. Now that we have our pieces, look closely. So we have that u is equal to cosine, so if we substitute this, we get u squared, then sine x dx cancel out, just replace with negative du. Then we have the natural log of cosine of x, which is simply just ln of u. But then we have the natural log of sine of x. So what we have to do to get the sine of x, get it in terms of u. So note that sine of x squared plus cosine of x squared is equal to 1. It's from our unit circle. Then we can actually solve for sine of x. So we can actually subtract cosine square of x from both sides. So we have this, and then just take the square root of both sides. So it's sine of x equals square root of 1 minus cosine square of x. And then you could just replace sine of x for here. And in terms of u, it's just the square root of 1 minus u squared. So now that we have that, let's actually replace everything with it. So I is equal to, and then we have to, and don't forget we also have to change our bounds as well, since we are doing a substitution. So as x equals 0, so cosine of 0 is equal to 1, and as cosine of, as x is equal to pi over 2, then cosine pi over 2 is 0. And because using our properties of definite integrals, because we have a smaller number as our upper bound and a bigger number as our lower bound, we can actually just switch the two, and meaning we also have to change the sign. So this will be a negative integral of from 0 to 1 of, and actually because we have a negative du, then the negatives cancel out, so then again it'll just be positive. It'll just be positive integral from 0 to 1 of the natural log of u times the natural log of 1, or natural log of the square root of 1 minus u squared, then divided by u squared du. And because we have a square root inside the natural log function, then we could use our rules for exponents, or our rules of natural logs, if I meant to say. Then we can actually move the 1/2 in front of the natural log, but then 1/2 is just constant, so we can actually just move that outside of the integral. So it's just 1/2 0 to 1 of ln of u multiplied by ln of 1 minus u squared u all over u squared du. Now, the next thing we're going to do now is we're actually going to use the natural log of 1 minus u squared and use its power series representation. So note that the ln of 1 minus u squared is equal to the summation from the index equals 1 to infinity of negative u to the 2n divided by n. And we can distribute out the summation symbol and the negative 1 over n. So that way we have negative 1 over 2 times the summation of 1 over n multiplied by the integral of 0 to 1 of n, because u square is the same thing as u raised to negative 2, so we can actually rewrite it as ln of u then multiplied by u to the 2n minus 2 du. Okay, cool. Now next thing we're going to do is we're going to do another substitution. So this time I'm going to let negative t equals the natural log of u. So we take the base e from both sides, so we get e to the negative t is equal to u, and then take its derivative for both sides, so it's du equals negative e to the negative t dt. And because the negatives cancel out when we substitute everything back in, then we would just have negative 1/2 sigma from n equals 1 to infinity 1 over n. And then we're changing our bounds of integration again, so when u is equal to 0, this actually converges to negative infinity, so we have negative t equals negative infinity, whereas t is equal to infinity. Then when 1 is equal to u is equal to 1, so ln of u is just 0, or ln of 1 is equal to 0. And because, again, using our properties of definite integrals, lower bound is the bigger number, the upper bound is the smaller number, change the boundaries, and then we get a positive. We have a positive sign now, so it's just positive 1/2 sigma of n equals 1 to infinity, and then 0 to infinity of negative t, then multiply by, we have our u, so it's e to the negative t raised to the 2n minus 2, and then e to the negative e to the negative t dt. And these signs will cancel out, so it'll just be positive. So rewrite this again another time. 1/2 sigma infinity n equals 1 over n. This is just t e raised to the, and I'm actually going to distribute the negative t to the exponent here, and then also combine the negative t from here together, so since they have the same base. So in other words, this is negative 2nt plus 2t then minus t dt. Alright, cool. So far so good. Now we can actually just simplify this out, so let me draw my arrow over here. So we have, so far I is equal to 1/2. Let's see, rewriting all this again. Infinity. 2t minus t, that's just positive t, so we factor out the negative t, so this is just t times e raised to the negative t, 2n, and then minus 1. There was a fly on my board. And then, guess what? We're actually going to be doing another substitution for the third time. So this time we're going to let u equals t times 2n minus 1. And because we're also going to need to replace something for t in terms of u, so that means when we solve for t, we have that t is equal to, or my bad, t is equal to u divided by 2n minus 1. And then when we take the derivative for this is just du is equal to 2n minus 1 dt, then divide the 2n minus 1 both sides, then we get du is equal to 2n minus 1 equals dt. And we can just substitute everything back in. Let's draw another arrow again. Then we have place everything 1/2 n equals equals 1 of 1 over n. And we're also changing our bounds again another time. So when t is equal to 0, this is just 0, so 0 here. And then when t is equal to infinity, this is also infinity, so nothing's changed. So then, now we have our pieces, we could just replace everything for in terms of u. So t, which is u divided by 2n minus 1, then times e raised to the negative u, and then multiply dt, which is du divided by 2n minus 1. And then combine everything together, sigma n equals 1, infinity, so it's just u to the u times e to the negative u divided by 2n minus 1 squared. And then because 2n minus 1 squared is just a constant, we can actually move that outside. I forgot to put the 1 divided by n. So let me actually just rewrite this, otherwise it's gonna bother. Let me rewrite this again, otherwise it's gonna bother me. And I'll explain it again just one more time. Okay, so 2n minus 1 squared, that's a constant. We can move that outside of the integral. So then this will just be 1/2 sigma infinity n equals 1 of 2n minus 1 integral from 0 to infinity of u du. Alright, so now here comes the easy part. This is calculus 2 right here, integration by parts. So simply, I'm going to let v, we're going to use our letters u, v, and w instead, since we have a u inside. So I'm going to let v equals u, so then dv is equal to du, and then dw equals e to the negative u du, then integrate both sides so we get w is equal to negative e to the negative u. Then we just plug our pieces together, v times w minus the integral of w times dv. So then we have negative u times e to the negative u minus minus the integral from e to the negative u e to the negative u then times du. Then I can just take the negative outside, so then this will just be a positive e to the negative u du. Then it's the same thing, so this is just e to the negative u. Evaluate that from infinity to 0. When you plug infinity, this is negative infinity times e to the negative infinity, which is 0, and then e to the negative infinity 0 again, so that'll just be 0. Then minus, we plug 0. This term's just 0, so we can just ignore that. Then e to the negative u is e to the negative 0, it's 1, so negative 1. So therefore, it's just equal to 1. So now that we have that, so far we have that I is equal to 1/2 times the sigma from n is equal to 1 to infinity of 1 divided by n times 2n minus 1. And we can actually distribute the 1/2 inside of the summation. So in other words, I is equal to 1/2, or oops, supposed to be the summation of infinity to n equals 1 of 1 divided by 2n times 2n minus 1. Okay, and now no more integrals we have to evaluate. So as of right now, the rest is going to be all with series. So this is where things will be getting a little bit interesting. So now what I'm going to do in this step is I'm going to be adding a 0 pair. So what I mean by that is I'm going to rewrite the 1 so that the numerator has in terms of n. So in other words, this one, so we have 2n minus 2n minus 1 divided by 2n divided by 2n times 2n minus 1. then we can actually split the summations into two different series. So we have the sigma from, can you see from here? Yeah, you can see. Okay, cool. N equals 1. So this will be 2n divided by 2n times 2n minus 1. That will cancel out, so it'll just be 1 divided by 2n minus 1. Then minus 2n, or yeah, sigma from infinity to n equals 1 of 2n minus 1 divided by 2n times 2n minus 1. So 2n minus 1, they cancel out, so it's just simply just 1 over 2n. Oh, I just realized I forgot to put a square. So that's a square here, square here, square here, square here, and then actually this piece will be 1 divided by n to n minus 1, like so. Okay, sorry about that. I knew I was missing something, but now I found what it was. Now, this series here actually converges to pi squared divided by 8. I'm not going to go over details about how to evaluate this, but the method you want to use in order to evaluate this series is using Fourier's method. So this actually equals pi squared divided by 8. So now the last thing we have to evaluate is this series here. So far we have pi squared divided by 8 minus sigma from infinity of n equals 1 of 1 divided by 2n times 2n minus 1. And then I'm actually going to do perform another adding a 0 pair second time. So just like before, it's pi squared divided by 8, then minus sigma n is equal to 1 of 2n minus 2n minus 1 divided by 2n times 2n minus 1. Okay, then same thing as before, we can split this up into two different series again a second time. So this will just cancel out to 1, which is just 1 divided by 2 minus 1, and then actually this will be a plus because we're distributing the negative. So n equals 1, and then 2n minus 1 cancels out, so it's just 1 divided by 2n. Then we can actually combine it together, so then we have this, just minus the sigma equals 1 of let me write, I'm going to put this in brackets, 2n minus 1, and then minus 1 divided by 2n. Okay, so far so good. So let's actually expand the series out. So I'm going to write this out manually as so. So we plug n equals 1 to here, so this is just 1 divided by 1, so it's just 1 minus 1/2, then plus, we do n equals 2, then you just do this so far, just keep going. So it's just 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6, and dot 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 so on. And then another way to actually rewrite this series is this piece here is actually the same thing as the summation from n is equal to 1 to infinity of -1 to the n plus 1 divided by n. And as you pay attention closely, this is actually an example of an alternating harmonic series. And I'm not going to go over the methods the second time how to evaluate this, but to do this, this actually converges to the natural log of 2, and you can solve this by using either the Riemann integral or the geometric series. You take your pick. So this converges to natural log of 2, so therefore we have pi squared divided by 8 minus ln of 2, which is equal to I. And we have our answer. I hate this heat.